Okay, just once more for the record. Let's talk about conservative fields. Really important. Electric fields, magnetic fields, gravitational fields, and many other fields are conservative. And in physical university. That means energy is in some sense. At least the energy that's associated with the work done by those fields is considered, even though those fields typically act in situations where there are other forces that are not considered. Okay, well, definition of conservative field is it's path independent. That's one characteristic. Okay. A conservative field is the gradient scalar function, and that scalar function called potential function. The acceleration of gravity in the vicinity of a planet is the gradient of a potential function. Okay. That potential function like big G squared out over R squared. I'm just get it back with the negative sign. Okay. And if you're in physics, you know that. If you're not in physics, ignore that. So you'll come to love it like everybody else. Okay. Well, in the abstract, that means you can take any old function of X, Y, and Z, calculate its gradient. We got to consider everything that's path independent. But what do I mean by path independent? Means that the line integral of f dot ds between 2 points. Points in the plane, 2 points in space, 2 points in coordinate space time. Well, don't want to do it. Okay. It means that this integral is independent of a path from A to B. So it means if you got point A here, point B here, take a straight line path, that's fine. Okay. Take a path parallel to the x-axis, parallel to the y-axis. Or take or any other path. Does that happen make sense? This is examples. This is enough to do examples. All you gotta do is take a scalar function, write down its gradient. And you got a problem. Says, okay, you guys, you do the integral over this path, you do the integral over that path, et cetera, et cetera. You're all gonna get the same thing if you do the integral right. And that kind of makes the point. We might actually do that, maybe not. We'll see. Okay. Another equivalent way to say this is this integral is 0 when it goes path, and by that little circle there, I mean closed path. Okay. Now, why would that be equivalent to this? Well, take the closed path. Remember where it started, where it stopped. Now take any 2 points on that path. Column A and B. Well, if you choose a direction along the path, and usually we choose a positive direction with our right hand, it takes some segment of the. See if the right hand rule gives you a positive or negative direction. So we go counterclockwise, but sometimes it's hard to figure out, really hard to figure out whether the thing is clockwise or counterclockwise. As a matter of fact, some curves on some spaces, that, for example, on a Möbius strip, you can't define clockwise or counterclockwise. Okay. What's clockwise becomes counterclockwise and go far enough. Stuff like that. We're not going to talk too much about that, but we talk about orientability. So an orientable curve is one where basically you can distinguish clockwise from counterclockwise in a consistent manner. Okay, well, we're going to take an interval from A to B. Along this path, call this path C1. And then I'm going to continue this path C2. Is that Sam Cooke or not? He wrote the song. He's got the smoothest voice that's ever occurred in the universe, and that doesn't sound smooth enough. Kind of slow, so there's no danger of my dancing to it, but it's still going to come. Okay. An awful lot laughing. Maybe it's just a speaker. Sam Cooke's biggest hits were very professional. First one was that's about 14. Okay. That was in college for time. Okay, anyhow. We got these 2 paths. And I'm claiming C1 plus C2 makes a closed path, right? So that's closed. That equals the integral along path C1 plus the integral over C2 of F dot ds, which in a sense equals the integral from A to B and integral from A to B of F ds plus an integral from B to A. Of F dot ds. Right? Because you're going from A to B, then you're going from B to A. Now, if the integral is path independent, the integral from A to B of F ds is the same for any path. Meaning the integral along this path has to be equal to the integral along this path because both paths go from A to B. But this is the backwards path along C2. So that when I increment the F dot ds going in this direction is negative of whatever it is going in this direction. So that these two have to be equal and opposite. I think they must have been. I write it really tiny. Saying okay, now what this says is just the integral from A to B. This is equal to the integral from A to B minus the integral A to B. Right. With a tiny. I'm going to rewrite the whole thing. Okay. So again, the closed interval over C1 plus C2 about dot ds equals the integral over C1 of F dot ds plus the integral over C2 of F dot ds. I read that neatly down here, but now when I wasn't able to write neatly, myself is this integral is then an integral from A to B of F dot ds plus an integral from B to A of F dot ds. Well, if you reverse direction, just think about what happens in a typical increment. If your ds is in this direction and your F dot ds has one value, if your ds is equal but in this direction, it has the opposite value. So your dot product will be negative of whatever it was when we go in the other direction. So this is the integral from A to B of F dot ds minus the integral from A to B. Of F dot ds. But when you reverse the direction of integration and in single variable, you know, if you reverse your limits in an integral, you get the negative. And hopefully you understand what an integral is well enough to know why. Okay. And hopefully now you understand what an integral line integral is well enough to know why. This works for line integrals too. Okay. We reverse the direction of our path, we get the negative, and of course, then this is just zero. So if F is conservative, then It's path independent. If it's path independent, then any closed curve can be broken into two subpaths. Okay, one of which goes from A to B, the other which goes from B to A. And if the thing is path independent, those are equal and opposite, you get zero. So never go over the closed curve. Have this on. Okay. Let's do a big thing. There's no board to do it, if you know. Yeah. We'll just do this in 2 dimensions, we do it in 3. So, rise, river, well, but 5F block. X squared plus y cubed. Let that be gradient. Okay, well, write down the gradient for me. I don't know if this thing's in focus. I kind of read it. Okay, don't go ahead and do that. Actually, put the board up. Okay. I think everybody's got it. That thing still doesn't look like it's. Camera is still about focusing. So I'm gonna kind of leave this in until we get more stuff. Okay, well. Picture right down the line, the James stuff. Some people just look at notation. Really great, whatever looks best for you, good for me. Okay, so now I want to do. From. Make it really easy. Go from 0, 0, and 1, 1. Okay. And we're going to do 3 paths. First path. Here. It's obvious. I mean, this would be vertical and consistent. It's a long way upside. Second path. Right here. And the third path. Right line. So set up the line and let's have Okay, now. I'm having a little more trouble with this than I would have anticipated, but I figured at least when we got here, we ran into some problems, so let's do this in a little more detail than I really wanted to. But I think we'll see what's going on. Okay, first of all, how do you do a line of parameterize your path? Okay, so let's just do this path. And now along this path, really, you don't have to do much of anything. We're going to do anything. You don't have to do much of anything because y is 0 everywhere on this path. So this is 0 everywhere on this path, and you're integrating the 0 field with 0 magnitude everywhere along this path. You're going to get 0. You've only got to worry about this path. Still, I'm going to parameterize it. Okay. So zero, 0 to 1, 0 along a straight line. Partition 0 less than or equal to x less than or equal to 1. Okay. Now I'm not going to write up the whole partition. Delta x is a vector. It's equal to delta x times I. Okay. So you can use x as your parameter. And the value of the function well, x is your parameter, x is what's changing. You got to evaluate f at x I star and then whatever y is. But that equals two x I star y cubed I plus 3x I squared y squared y. Okay. But y is 0. Y is 0 everywhere in this path. Okay. Now follow that same reasoning. And of course, you're going to get an analogous thing if you're doing this path, right? Because x is 0. But now, if you're doing this path, you're going to have to parameterize path from here to here, from 1 0 to 1 1. Okay. So what's your parameter going to be? Well, thing that's changing is y, so just let y be your parameter. We're not doing an arc or anything like that. We're doing a straight line, so that's going to work. Okay, and if you're doing this one, you're just gonna let X be your parameter. So start with your typical increment. What happens on your typical increment? Because you don't have your typical increment, you're gonna get managed. Now you get something pretty close. Okay, get something pretty reasonable, but you're not doing a dot product of anything because you don't have a DS. Okay? That makes sense? So see what you get. Do this. Let's be real formal like this. Path can be characterized by the fact that y equals 1 and x is between 0 and 1. So typical increment. I'm not seeing this in anybody's paper. Really, what this step you gotta have it in order to do a complicated alignment. Okay. Now it looks like everybody's. I think you're done the assignment of line makers. Okay. Do the thing, everybody got a perfect score on it. Nobody's doing this. I think that's going to cause the talk to this chapter. Come down with at least focus on a typical. Okay. So typical increment, I'm not even going to use R's, I'm going to use what have a delta X. Put an eye on it. Okay. That math took on your own. Consistency. Delta S is delta X on. When I first threw this out, nobody had delta S's. Okay. First of all, y is 1, so replace y with 1. If I end up with a y in my integral, something's seriously wrong. Okay. Now I might do the integral because I could do the integral with y in there. And maybe at the end I realize, oh, duh, y is 1. Okay. You can do it later, but you better do it early. You better get typical increment rigorously correct. Then the integral becomes very easy. Now the integration might or might not be easy. In this case, it's really easy. At least try out the integral. Start with the integral. You develop the integral. You don't shortcut it. Acting like engineering. Oh yeah, that's what you're going to be. Well, get over that. Okay. Because you're going to be better engineers if you know how to develop an integral. Have a machine to do the integration for you. You won't have the machine unless ChatGPT gets a whole lot better. Pretty darn good already. You're not going to have a machine to set up that for you. Okay, so now that's I star 1. is just two X Y plus three X squared J. Agree? One. You got two X I and three Y squared, three X squared J. That's not there else. Equals. Don't have to write it all out. It's obvious you write this dotted with this, and you're gonna get two X delta X. Okay. Most of you ended up with a three X squared in the middle. Okay. If that three X squared is in this direction, you're integrating in this direction. You're integrating a dot product. You're integrating a vector in this direction, dotted with a vector in this direction. You get zero. Now, you do have a component that's in the same direction, so the dot product is going to give you that. So, writing this out, tend to get it right. Not writing it out, you miss details. That's all there is to it. All this half C2. The interval over C2 from 0 to 1. That's 2x dx. You can do that one in your head. And you get two things. No, you don't get an x squared over 2, you get 1. See the danger of doing it in your head. Okay. The x squared in my head. It's really 1/3 thing from it. I look at what I'm actually doing, right? I have to change it, right? Okay. We agree with that. That should be 1. And I've lived with 2x in the x squared. Okay. Now over C1. I haven't written the complete integral. But we observe that the integral from here to here has to be 0 because the function is 0. And I should have said 0 plus. I don't have room to write it. So anyhow, we're going to go ahead and do this. 1, 0 to 1, 1 along a straight line. Well, long story short, we're going to end up integrating 3y squared dy, and it's going to give us 1 again. Which illustrates, at least it is believable, that this is path independent, as it has to be because it's a gradient. That's what we're really trying to do, but we're spending too much time messing with the line. You know, got to get better at that. Okay, so from 1, 0 to 1, 1. I'm just going to write this down. Typical increment, you have a delta Y sub I. Y sub I star. Remind ourselves that X equals 1, not a bad idea, although we wrote it down there, and we should be aware of it, but, you know, with experience, you get better, you get more aware, okay? And you'll have experience in this section because you're gonna have to do these things. Okay. So. Delta S equals delta Yj. Has nothing to do with this trade. F of X Yj is two Y cubed I plus 3Y squared J. F dot delta S is just 2Y squared I. There's no I component here. Of course, your I component is perpendicular to the path. So obviously that path's going to get 0 out of the I component, and then it's just going to have 3Y squared delta Y. We're going to go over C1 of F dot ds equals I'm going to write the 0. I should have written here the 0 corresponding to the this part of the interval. Okay, which we did over here. And I not it's 3Y squared dy equals 1. And we verify that this interval is equal to this. That doesn't prove that the interval is the function is path independent. But it verifies that at least for these two paths, makes it appear to be so. Okay, you'll have problems. Something has to do that for different fields and different curves, and they aren't all straight lines. Now let's do this. I want to see the typical increment. I want to see a parameter. Okay. So I want you to first parameterize that path. And I'm going to ask you to do it using T as your parameter. Because that should be familiar and it should reinforce something you really need to be aware of. Okay, I can't emphasize enough. Parameterization is where it starts. And it's where the hard stuff that we're going to get to in the next week starts. You got to be able to parameterize one dimension before you start even thinking about parameterizing in 2 or 3 dimensions. And everybody needs to get a little better at it. Some people need to get a lot better at it. Once you have a parameterization, everything falls out in pretty much the same way, just with different expressions. And so we want to parameterize this path, straight line from 0, 0 to 1 there. We made a straight line there. There's the parameterization. Okay. Then. Typical increment would be a delta TI with TI star. Point. The point. So, like this. Well, I think it might be a little confusing. That says xi minus one, yi minus one, which equals then ti minus one, ti minus one, right? So that's then from here to here, right? Your delta S is ti minus one, ti minus one I, ti minus ti minus ti. Delta S is ti minus one I distributed plus ti minus one j. Now, that's a bunch of symbols. What the heck is the theta means? You're on this path. Somewhere on this path, you have an increment here. Coordinates of this are ti minus one, ti minus one. Coordinates here are ti. I would love to see a picture. Instead of just bunch of symbols. Because I think everybody missed at least one important thing, which is maybe not. So anyhow, there's your delta S, right? And of course, I could write that as delta Ti times I plus delta Ti times J. Now we've got a delta S, and of course then F. Well, F is 2x cubed I, that's going to be 2 times Ti times Ti cubed times your I vector plus 3 Ti squared times Ti squared times your J vector. That simply equals 5. The item the fourth. No, it'll come out that way later. We are gonna get something like that, but not. It's. Two TI to the fourth I. Plus 3 TI to the fourth. Okay, obviously, we can have those. Okay. Well, what we want to integrate is F dot DS. F dot del X. So that. Approaching like crazy on my previous work. Still the TI times the I vector plus still the TI times the J vector. Okay. And that's not an IJ substitute. You should understand that if you write the sum, you'll get it right. And then the dot product is then 2 TI to the fourth. Delta TI plus 3 TI to the fourth. Delta TI. Which equals 5 TI to the fourth. Delta TI. Well, then the sum of all these, which is the integral of 5 t to the fourth dt. Okay, at least one person got it. I thought it was a fountain. So the integral over half C3, which I will label a little bit later here, C3. And is that, yeah, okay. So the integral over C3 F dot ds because of all this equals the integral equals 0 to t equals 1 dot 5 t to the fourth dt, which is 1 again. Okay. Now I could have to ask you to integrate this over the arc of the circle center at the point 1/2 of radius. Half the square root of 2. Square root of 2 over 2. Okay. Be an arc here. I could ask you to do it over parabola here to here, where x would equal t and y would equal t squared. Okay. I could ask you to do it over the inverted parabola here. Okay. Where x would equal t and y would equal t minus t squared. Okay. You need to be able to do these parameters. And you need to focus on the increment so that you get the right answer. Don't just fish around until you get something that gives you the right answer. Do it rigorously. Okay. I was going to way too much time on this one example, but we really have to get the presentation down. Really, really, really important. Okay, well, anyhow, this at least demonstrates in this one case, which again is apparent path of dependence. You can't check it over every possible path. You just have to prove this. I'm going to talk about how we prove it. I'll talk about how. Okay. Suppose we don't know that this is a potential function. How would we figure it out? From the form of the function. Okay. How can we find pi if we don't already know it? And is there any point in even trying to find pi? Well, I'm gonna find it. If this is a potential function, its curl is zero. So you test first of all, if the curl is zero, then you know, you have. That's a potential function. Yeah, you know you're gonna get a potential function to get one. Theoretically, if there is one, might not be able to get it. There is one. So you're gonna have to get me read what through some of that. Well, find it. Okay. We're gonna let up with 0, 0 equal I plus 7j. No. I can let it equal any constant. Okay, that's constant vector. Now, the easy thing would be to let it equal the 0 vector. I want to demonstrate briefly what happens. Okay, so I have to do this kind of figure. Okay, well, then. F of x y is going to equal. Trying to just think what notation. Use for it. It's very much like what you did differential equations when you're solving an exact equation. Okay. You're going to find an antiderivative of this vector function. That's next line is going to be F1I plus F2J. F1 is phi sub x, F2 is phi. Derivative of phi with respect to x. This is the derivative of phi with respect to y. That seems familiar. Review what you did with it. It should be, and it might become familiar as I do. So we have this. Of course, what is F1? F is F1I plus F2J. F1 is this, F2 is this, right? But I want to write the division. Okay, well. So. Five, it doesn't have to be an integral. And I agree with. Of F. With respect to X. Which would be an integral. Of one with respect to X, okay? Which would be an integral of 2x y cubed with respect to X. Which is x squared y cubed. Okay. Well, we just kind of got it. Equals 5 squared y cubed, right? That's what you see from those. It's identical. Just different context. You do exactly the same thing. Now, they're going to have 2 dy better be in agreement with this, right? Okay, now, another thing. We're integrating with respect to X. Your integration constant is a function of y when you integrate with respect to X, right? I mean, you have an integration constant, then put it down because you're not going to need it in this case, but let's be sure we have a method to get it for us, okay? So your integral of f2 dy is the integral of 3x y squared. Written down, where is it? X squared y squared dy, which equals x squared y cubed plus h of x, because it has this function of x, right? And you're going to need these functions most of the time. But in this case, we have only one term in our original 5. So that and we can write this, and this is true. If g of y is identically equal to h of x, which it can be, as long as both of these are constant. Okay, so equals x squared y cubed plus a constant. Now, the 5 we started with didn't have, well, it had a constant, but it was 0. That'll often be the case. Now, if I'd have started with this, well, my integrals, my g of x and my h of, my g of y and my h of x would have then had to agree with these, and they would have. I do the derivative of this. If y was this, then f would be 2x y cubed minus 5x to the fourth I plus 3x squared y squared plus 2y. Okay, and our integrals would have gotten us back to this. Plus maybe some constant. Make sense? Again, that should be familiar, and that part of the operations give you no trouble. No, we didn't get to go over as much as I wanted to. And we'll probably talk a little bit more about it after you've done the assignment. But above all, please parameterize things and focus on an increment. Get in the habit of doing that, even if the problems are low ball easy, which I think they tend to be too much of in the web of science. Not always, they have some good problems. Okay. Make sure you can do challenging problems by following a valid method with no shortcuts. Good luck. Have a great weekend.